Hello and welcome to today's webinar. My name is Tyler Reid. I'm the Manufacturing Application Manager here at GoEngineer. And today's topic is SolidThinking Inspire. Analyze first, design second. We're going to be talking about the workflow for using Inspire and topology optimization and shape optimization and how it's different than your typical design and then simulate process. So I thought I would introduce SolidThinking to start off with. It is one of our newer vendors, and they've been a great partner with us. We are offering about 7 different products. The Inspire product that we're going to be talking about today. There's also some casting, extrusion, and forming prediction pieces of software called Click to Cast or Click to Extrude or Click to Form. And then also some embedded system software, Compose, Activate, and Embed. But primarily SolidThinking is a NURBS CAD tool. So let's talk about topology optimization. Topology optimization, sometimes called shaped optimization, is a really true design for additive manufacturing technology. The algorithms and the tools that are in use within the Inspire software have actually been around for quite a while, but they were always ahead of the manufacturing capabilities. The results out of these pieces of software would create shapes that were typically unmanufacturable by conventional means. But with the growth that we've seen in 3D printing and particularly engineering-grade plastics and metal printing for production parts, we've been able to take advantage of these topology optimization algorithms. We will also see Inspire has tools for conventional manufacturing as well. So whether you're machining or casting or injection molding or extruding your parts, you can still take advantage of this software. The biggest difference with designing with topology optimization is that the engineer or the designer, instead of taking their best guess at a shape and then simulating afterwards and refining through that process, they simply define boundary conditions, mainly a working envelope, load cases, and then they let the tool whittle down the shape based on the critical geometry that's needed and the working envelope. So they essentially set up an FEA study and let the software come up with the first guess for a shape. And then that first guess is built upon in your main CAD tool, and more intense or more stringent FEA is done later on. But it eliminates that first step and it really speeds up the design process. The big takeaway here is that the software outputs the load paths so that the engineer or the designer knows where it's most important to have material and where it would be excessive or unnecessary to have material. And for that reason, we're able to take new designs or existing designs and make them lighter and stiffer at the same time. Within Inspire, we can optimize for different characteristics. We can maximize stiffness. So we could say, here's an existing part or here's a prospective part. We need to maximize the stiffness without adding any mass and really minimizing the mass. We could also target a mass or run a study that minimizes the mass. So we can set, say, a factor of safety of 1 to whatever number we'd like, and then tell it to minimize the mass down to that factor of safety. We can optimize for resonant frequencies, the normal modes, and we can also optimize for wall thickness. Now, this is what I was mentioning before. We have the concept of shape controls. We can go without any shape controls, and that's going to give us a very organic result that might only be manufacturable through additive means. Or we can apply some rules, and we can do an extrusion-based shape control or a single or double draw molding shape control. The process that we're going to walk through is pretty similar to what you see on the right-hand side. We start with an existing shape. That looks like an existing part with some ribbing and whatnot. If the existing part had ribbing like that, we would usually remove the ribbing and let it just be a solid design envelope. Then we set up the studies. and run a shape optimization. And that will give us the result in number 2 that you see there. And then we run an FEA analysis on that optimized shape. Inspire is a growing tool. New with Inspire 2017, we now have motion studies. So we could always bring in assemblies and adjust the contacts between assemblies and whatnot, but we can never really create motion within those assemblies and then use that motion analysis to develop loads and forces. But we can now do that within 2017. I'm not going to cover it in this webinar. It's going to be a subsequent webinar, but it's really cool. It's very similar to the SOLIDWORKS motion studies, where if you know the motors, if you know the actuators, if you know the weights and how parts move together, you could swing a robotic arm through a motion and then develop a load scenario for different components of your robot. And then we can feed that load scenario into our optimization. It also will do topography optimization now. So I've been talking about topology optimization, which is shape optimization. Topography is optimization of surfaces, adding beads or swages to increase the stiffness of a surface. So if you wanted to increase the stiffness of, say, a sheet metal component through different form dies or pressing operations to get the nice shape, we can now do that as well. And also we can do bolt pretension, which just gives us a little bit more accurate analysis and optimization results. So this is a tool that's growing. Every new version has a lot of new tools, and it's a very exciting platform to be working with. To kind of walk you through those basic steps visually before we jump into the software, I put together a couple slides. This is from a project I did last summer. It's for an RC car. What you're looking at here is the design space for the RC car chassis. You see gray components and you see red components. The gray components are what I call the critical geometry. These are our mounting surfaces. In the case of this car, it's where the shock's mounted, the control arms mounted, where the motor mounted. And then everything else, the red, is possible design envelope. So whatever my chassis is going to look like, it has to fit within that red space. So this is what we start with within Inspire. Now you'll see we can draw these shapes within Inspire, or we could draw them in another CAD tool and import them into Inspire. That's what I did in this case. This was drawn in SOLIDWORKS because it's a pretty complex shape, and that's what I was most familiar with. Then we start to build up load cases. So these are the FEA studies. Now load cases, if you're familiar with FEA analysis, this is going to be pretty similar. You have loads, you have supports, you have fasteners, you have joints, you have contacts, all of that stuff you'd have. What's cool within Inspire is you can actually do different load scenarios. So in the case of the car, I knew there would be times that it would be accelerating. I knew other times it would be decelerating. And in other times it would be doing hard turns. And so I actually created 3 separate sets of loads: acceleration, hard braking or deceleration, and sharp turns. And each of those have different forces, different accelerations, different torques. And Inspire actually solves an optimal shape for all 3 of those at the same time. That is awesome. And that's something that is pretty unique to this type of shape optimization software. You can also apply shape controls. They can be as simple as symmetry planes. Those symmetry planes could be planar or cyclical, or they could be manufacturing based like we talked about. They could be extrusion based or single or double draw. You can run an analysis at that point to get an idea. So this is a plain FEA analysis, and then you can run what we call an optimization analysis or a shape analysis, and that's where we're going to talk about the details here, but this is the shape analysis portion. Once you get the basic shape, then the software has now told you, based on your loads, your expected loads, This is where you absolutely need material. Now, you can add more material. You're going to be less optimized, but this is where you absolutely need the material. How you get it there is up to you. It might be cast, it might be machined, it might be printed, it might be a weldment, but this is where you need the material. Inspire does have a tool called POLYNURBS, which is a direct editing push-pull type tool that allows you to start to use those load paths to guide a very smooth organic shape. We'll talk a little bit about those during this webinar, but it will probably be a whole nother webinar where we talk about it in depth. So let's jump into the software. I'm going to go over a very basic setup, and then we're going to go over some results of a part I've been running over the past couple days. So this is the basic interface. We have some geometry tools available to us, so we can do drawing within Inspire. We have our structure tools, which are our load and FEA analysis setup. We have our motion tools and stamping tools as well. So geometry creation and drawing, it's not too difficult. It's actually pretty user-friendly. I'm going to go ahead and create sort of like a boundary box here. Simply sketch, and then it becomes a push-pull type situation. So I can push and pull it to the size I want. I can click that interior face and pull it down. So I just created an empty box. If I wanted to create a box or a design space to optimize within this, I can click on a face, hold Shift, and pull up off that face. Now I'm creating a second body off that existing face. So I now have two bodies. And over here on the left-hand side, I can see the different bodies in my model. There's the inside body, and there's the outside body. Now the inside body, this might be a part that maybe it will be supported on one side and pulled from the other side, and I want to know what the optimum shape would look like within the center. So this would be what we call our design space. This is the space that Inspire can whittle down. Okay, so this will be the area that actually gets optimized. Now there are some other tools within here. We can have all our basic sketching tools. We have some Boolean tools. Adding or subtracting bodies from one another, mirroring, cutting, simplifying parts. It has some built-in tools, like if you bring in an existing part that already has ribbing or already has holes and you want to just simply get rid of those, simplified geometry will do that. And fillets and mid-surfaces and whatnot. So if I wanted to create some holes on this side of the face, I'd simply select my sketch tool, then select my face, and I can draw a hole. We'll say it's a 1-inch diameter hole, and we'll draw another guy here, 1-inch diameter. So we got two holes there. To create a cut out of those, I would simply pull the face out. That's kind of how it works here. So this is my basic shape. Now if I want to start setting up an FEA study, I go to the structure, and we're going to talk about each of the options here in a little bit more detail. We have fasteners, okay? Fasteners connect parts together. So examples of fasteners, if I click on here, would be a nut and bolt, a grounded bolt, a screw, and a grounded screw. Okay, so fasteners connect parts and do not allow movement between the two. Joints connect parts and they do allow movement between the two. So examples of joints would be things like pins or hinges. Okay, and each of those joints can be locked, they can be active, they can be free. This is how we specify how different parts are connected to one another. The last type of connection is called a contact, and this is simply bonded, contacting, or no contact. okay? And this is what we're going to have in this case. This will be a simple bonded contact. That's the default, so I don't have to touch anything in this scenario. We also have this idea of connectors, which I'll talk about in the next part. Then we get to the setup. Notice as I hover over these icons at the top, each icon actually has several different options depending on what arrow I hover over. I kind of like this. It makes the menu very minimal. So under loads, I have supports, which we'll start with. To add a support, I can click on a face, an edge, a cylinder. If I were to click on the inside cylinder, it adds a support, which means it's basically that cylinder is going to be locked down. Okay. Right now it's locked down on the cylinder. At any point, I could just apply it to a single point within that. I also can apply degrees of freedom if I want to. So after I apply the support, if I double click on it, I could add a degree of freedom. So if I add this degree to freedom, it has axial freedom. If I had this degree to freedom, then this circle or this cylindrical face is free to spin. All right. Faces can also be supported. If I add a support that I would not like, I can come over to my model browser and I can simply delete it or deactivate it. A similar way of supporting this, we're acting as if this is maybe bolted to a wall, would have been a fastener, a single hole fastener, and a grounded screw would have done the exact same thing as this. Okay. So now we might add a force. Forces can also be applied to different types of entities. They can be applied to points, to faces, to edges. If I were to apply a force to this face, I can set the value of that force. So this is 1,200 pounds. I can set the direction. I can adjust the angle and position of that force. I can set it in to be just aligned to XYZ, or if I wanted components, I could do XYZ components. I can also do, I click this on the face, so it's applied to the face right now. I could apply it to the particular point I clicked on, but there's also other types of forces. If I were to click on a cylindrical hole, like on this other side here, it would center the force with the hole, but I could also do bearing forces. So if there was a bearing in here and we knew it was going to be strained in just one direction, we can simulate that. We can also do what are called traction forces, or these would be more like frictional forces. These are forces that are tangent to whatever wall we're selecting. So for example, let's get rid of this force here. This force, if we were to double click on it, we could change this to a traction force, and then it would be as if it was sliding against another component, like a frictional force. We're going to go ahead and just set this to be on the face and aligned with X. Okay. We also have torques and pressures, and nothing too fancy about those. Torques would be twisting forces, and pressures would be forces that are normal to the faces, spread out over the area of the face. Coming over to the next tab, we have displacement constraints. We have two different types of displacement constraints. One is a forced displacement. So if I wanted to impart a force on this face here, and I don't know exactly what force I'm going to impart, but I know I'm going to use enough force to move it a certain amount, then I can use a force displacement. Okay? So if I had, say, some sort of clip or buckle or snap fit where I know the part is going to have to move a certain amount in order to activate, this would be a good way to simulate that. We also have a displacement constraint, which is essentially a limit on the constraint. It doesn't impart a force, it's more of a limit. And then we have accelerations. We have linear accelerations expressed with an g value, or we have angular accelerations, which can have both a value and an acceleration rate or deceleration rate. So we would have the velocity and the actual acceleration and deceleration. We can impart gravity. We can set gravity to be whatever direction we need. We can do temperature loads. Okay, so once we set the material, Inspire knows the coefficient of thermal expansion. So if we know that it's going to undergo a temperature change of 50 or 100 degrees, we can impart that type of load. We can also do remote masses. Okay. And then we have some shape controls. So I have my single force and it's supported on this side. Under shape controls, I have symmetry. So basic symmetry would look like this, and I can simply select or deselect planes of symmetry that I would like to keep. Or I can do manufacturing shape controls, the single draw, split draw, or extrusion. And we're going to go over some results of each one of those in a bit here. I'm going to go ahead and stick with just the symmetry. Now we get to the analysis part. We have two types of analysis. We have just an FEA analysis, which is going to give us the results of, say, percent yield, tension and compression, von Mises stress, yield stress, typical results. And then we have our shape optimization. I typically run this first. Okay, so we can give this a name if we'd like. Then we set an objective. So our objective can be maximize the stiffness or minimize the mass. Maximize the stiffness is what we generally start with, and that's going to give us the load paths of the part. Now, when you select maximize stiffness, you are going to set a target for the mass or the volume. Okay, so standard default would be 30%, which means it is going to try to whittle down the design space to 30% of the original value. We typically start with that, and then based on the results, we might go up or down from there. Not uncommon to run multiple iterations of the analysis to get a good result. So I'll stick with 30 for now. Then we can add frequency constraints. We can maximize the frequency. We can minimize the frequency. If we could set a minimum, and then we could also apply it to so many multiples of modes. Or we can select none. Our thickness constraint is sort of like our meshing constraint. Now, I hesitate to call it that because the numbers are much more coarse than we would typically use in a mesher. And this number is a little bit fluid. So right now it's about 1/4 inch. I'm going to bump it up to 0.30. Our contacts are going to be sliding only. Gravity, we will just keep off for now. And our load cases, we only have one load case. So I'm going to go ahead and run this. When I say run, it gives me a warning and says optimization may take longer than 15 minutes. I'm going to go ahead and cancel that. We don't got 15 minutes. So I'm going to bump up the thickness constraint and then let this run. So I'm going to do a little bit more coarse run. While that's running, and it should go fairly quickly, this solver is quite rapid. But while this is running, I'm going to talk about another part that I have loaded up. So this part originated in SolidWorks, and it's a little stand. And within SolidWorks, I created a multi-body part. So we have 4 bodies on each corner. Those are going to be the supports for this stand. We have the main body, and if I hide this guy, and then we have this body at the top, which is going to be the interface for the stand. We're going to have some wire rope being connected, fastened to these different holes, and these wire ropes will be pulled in different directions, is kind of the function of this part. This is the full design envelope. Whatever part I end up with has to fit within this full design envelope. Okay, so I save this, and then I actually just open up the SolidWorks file within or Inspire. So it can open up a SolidWorks file. Within Inspire, I have to create or I have to set certain bodies as design spaces. So this would be my design space. I set the material over here in the drop-down menu. We have a basic library of steels, stainless steels, aluminum, titanium, magnesium, lots of different steel alloys, and some plastics. You can also create your own materials. I have an Ultem material for analyzing some of our 3D printed components. Very easy to create a custom material. You just need the modulus of elasticity, Poisson's ratio, density, yield stress, and coefficient of thermal expansion. And then we start applying loads. Now in this part, I actually have 3 load cases. So in the first load case, we're supported, just simply supported on the bottom of the part. And then we have vertical forces, each 200-pound magnitude, centered in these holes. That's load scenario 1. So in this scenario, the cables are being pulled straight up. In load case 2, we have a force that looks like this. So it's actually offset from the part, and it's acting on this face of the model. At an angle. Okay. And for the shape controls, I ran through this several different times. So we have different shape controls. I'm going to show you the different results. But we did each type of manufacturing shape control and symmetric shape controls. And then for the very last study, I add a third force, which was a torque raised up above the face. Before we look at that, I want to discuss the results of this guy that we just ran. So this is finished. We're going to go ahead and view the results now. So notice on the right-hand side, we have a slider, okay? And the slider is centered. Right now, the slider is centered at our target mass, which was 30% of the original mass. Now, 30% was our guess. Okay, we don't know if 10% would have been enough or if it needed 80%. We're not sure. So the function of this slider is to allow us to kind of get a feel for what would work. Okay? Now, if I had a situation where at 30% it looked like this, then I might rerun the study at 40 or 50 or 60%. Or if 30% looked more like this, then I might run it again at a lower percentage. So the idea here is that by using this slider and through a couple different iterations, we can actually see the load paths. Now, once we find a shape that we're comfortable with, then we can run an FEA analysis on it using this Analyze button. And the Analyze button is going to run a quick FEA analysis, and we're going to be able to see the factor of safety, the yield stresses, the displacement, where we have tension and where we have compression. So that was fairly quick. That's done. So if we look at the displacement plot, not a lot of displacement, 7.5 times 10 to the minus 5. Factor of safety is going to be pretty high on the entire part. Percent yield, tension and compression. Areas that are orange are in tension. Areas that are in green are in compression. Our max shear stress. Our von Mises stress. And the major principal stress. Each one of these can be animated. We can have call-outs. We can show the min and the max very simply. If we do a call-out wherever our cursor is, it will give us the value, so we can kind of probe in here. So that's kind of what that process would look like. And then if I wanted to, I could come back and run a second optimization. If I run second optimization, I might want to keep the same controls, or I might want to remove the controls. For example, this had a symmetric control. Maybe I don't need it symmetric. So I'm going to go ahead and delete that shape control. And we'll let this run again in the background without a symmetric shape control, and we'll see what how the results differ. Headed back to this part. Let's look at some of the results I've done. The first result was based off a max stiffness study targeting 30% of the stiffness. This had symmetric in the vertical and horizontal plane from this view. Okay, and we can see that in the results. Now, if I bump that down to 20% and added a shape control, this is the result. So this is the result of a 20% 20% mass reduction, and the shape control was an extrusion, okay, which means that it had to be solid and complete in one direction, and that's this top direction here. So this could be like an aluminum extrusion type shape, or it could be a machine shape. But we can see how this is whittled down in the corners and in the center. Changing it up again, this is also a 20% value, but this is with a single draw. So you can see a very similar shape, but it no longer had to be an extrusion. It just had to draw in one direction. Okay. Now, a lot of times, once you get a result like this and you know that your values are good and you're in the right ballpark, then you might run a minimize mass study. So minimize mass is a different objective. And when we minimize mass, we don't target a volume reduction. We target a minimum factor of safety. Okay. And for this reason, because we are dealing with factors of safety, it's really important that our loads are accurate. When we're doing stiffness, our loads don't necessarily have to be accurate. They just have to be relative to each other. So, for example, in our last study, in this shape here, whether or not this load is 5 pounds or 5,000 pounds, the shape that gives the maximum stiffness at, say, 30% is going to be the same, because that's the load path. But the factor of safety is going to be very different if this is 5 pounds or 5,000 pounds. That's an important concept that is not extremely obvious when we're doing these types of studies. So minimize mass, we set a safety factor. And I've done some minimize mass studies here. So the first result looked like this. This was a minimum factor of safety of 1.2. Pretty spindly. But that is the minimum mass that we needed to reach a factor of safety of 1.2. Very different shape than the maximized stiffness. This study here, this was with a different shape control. This was with a single draw shape control, a factor of safety of 1.1. Notice that the boss on the left-hand side is thicker than the boss on the right-hand side, and that's because of that angled force. Okay, so that's the main difference between minimized mass and maximized stiffness. Maximized stiffness is looking at the load paths, and it's going to do the shape. Minimized mass is looking at factors of safety. Now, I said later on I added a third load scenario, which was a torque. I ended up getting a little bit different result after adding that torque. This is still at 20% max stiffness. Let's take a quick look at this last part. Let's see if this guy is finished. It has. So remember, we ran this first with a symmetry line. Now we ran it without a symmetry line. And the result looks essentially the same. So it looks like symmetric is about the way it's going to want to go. So what do we do when we get to this point? Okay, we now have this shape, and we kind of have an idea of what's going to be the optimal usage of our material. What do we do from here? Well, we can use the POLYNURBS tool within Inspire to start to draw a part. I can save this shape out and open it up in my CAD tool and use it as a guide to draw a part how I would like to. Or I could save this out and print it directly. Let me give you a quick look at what a POLYNURB process would look like. We'll start with something like this. So the POLYNURBS tool is actually pretty cool because it lets us create these organic shapes using direct editing tools and tying into these load paths or the shape results. So when I have spindly arms like this, I can actually use these and interact with these results. Okay, so I'm creating NURBS bodies that I can then control by moving, expanding, shrinking, edges, faces, loops, etc. So if I build out a few of these guys, and notice it's adjusting to the current cross section of my shape results. I can take portions of these and move them. And it all moves organically and smoothly. Okay. I can bridge from one side to the other. I can add extra control points. So by adding these extra control points, I can then bridge, say, from this face to this face. And from this face to this face. And then by selecting faces within here, I can adjust the shape of these. So it's a little bit different, especially if you're coming from a parametric CAD tool. It's a little bit different adjusting these, pushing and pulling them. but allows us to create shapes that are very difficult to do normally. And then we could export that to our CAD tool of choice. So we'll do a more in-depth webinar on POLYNURBS later on, but I wanted to give you guys a sneak preview of what that would look like and how simple it is to use. It's really fun, and with little practice, we can create some really gnarly shapes. So if it wasn't clear, we do all the detail work in our CAD tool, whether that's SolidWorks or CATIA or what have you. All of the detail work happens in the next CAD tool. Inspire comes at the beginning of the design process. It's used to simulate first, create an optimum shape that you can then build off of, and it eliminates that first pass. It can be used to redesign existing parts, like you see here from Liebherr Group. They have a bracket that is for a spring, an air spring on a heavy-duty truck. So they have 3 axles. Each axle has 2 of these air springs. They were able to take the existing cast design, redesign it, and reduce the mass by 55% with the same performance. We see this a lot in vehicles, and a lot of what we're targeting here is mass reduction at the same performance. Mass reduction oftentimes means less material cost. It also can mean less manufacturing cost, better fuel mileage, 30% mass reduction on a steering arm linkage from Scania. Here's a bicycle crank from Raceface. They redesigned a part that used to be machined. This part had been available for quite a while, and they felt like they had pretty much optimized it as much as possible. But once they brought on Inspire, they were actually able to find a crank design that increased the stiffness by 25 to 50%, which is pretty impressive. Here's a part from a pile driver. This is a very large part. It's about 3 feet tall, very large, heavy part. The customer was having issues with this part failing, and so 3D Hub, a company out of New Zealand, used Inspire to redesign it. They were able to not only make it 30% stronger, but also reduce the mass by 20%. So that's just a no-brainer. When you reduce the mass, then the strain on the rest of the assembly is less, the strain on the motors is less, the bearings, not only reducing the mass by 20%, but also strengthening it at the same time so that it's no longer failing. That's awesome. A lot of Formula SAE teams are starting to use topology optimization with Inspire to redesign parts of all sorts. I've seen wheel hubs. This happens to be a steering hub, steering wheel column, I should say. Reduce the mass by 35% while increasing the stiffness 5 times. Wow. So thank you guys for joining in that quick start. Like I said, we're going to be doing a whole webinar series probing every aspect of this software, and we have some events coming up featuring it as well. If you have any questions about Inspire, definitely let me know. You can shoot me an email or comment on the YouTube comments. I watch all those. And I appreciate you guys coming. Thank you.